Okay, so what I want to do in this video is to pick up on the Y2O3 Rietveld refinement example and look at ways of improving the peak shape description. So if you remember the refinement that we did on yttrium oxide, we used an empirical peak shape approach where we fitted a pseudo-Voigt peak shape function to the experimental data. And we actually refined 5 quantities, 5 parameters in the peak shape, plus an extra parameter to describe the peak asymmetry. And at the end of the refinement, we had a fit something like the one on the screen here. We were doing a pretty good job of fitting the observed data with our calculated model. But actually, if we looked in detail, we weren't fitting the peak shape precisely correctly. If we looked at the difference curve wasn't flat across the peak shape. And in fact, in many cases, this won't matter. If you're doing just purely structural work or you're just doing quantitative Rietveld analysis, what you're interested in is the overall integrated intensity of the peak. So it won't matter if in some parts of the peak shape you're over-calculating the intensity and in other parts you're under-calculating intensity, as long as the overall area is correct. But there are other areas where it is really important to get the peak shape precisely right. So I want to have a quick look at another way of describing peak shapes. And that other way is to use what's called the fundamental parameters approach. And so what we're going to do is we're going to be using this equation at the top of the slide here. And what we're essentially saying is that the peak shape as a function of 2 theta depends on 3 contributions. There are contributions due to the radiation source we're using, so that could be our X-ray tube or the synchrotron source, or if we're doing neutron diffraction, the constant wavelength neutrons that come from a reactor or the neutrons that come from a time of flight moderator. There'll be contributions from the instrument, so it could be the slits or the optics that we use in a lab diffractometer. There will be contributions from the type of detector that we're using, and there'll also be contributions from the sample. The 2 of the most important contributions from the sample are these cartoons in the bottom left. The domain size, the coherent domain size giving rise to the diffraction pattern will influence the peak shape. So if you have very small domains, for example, in a nanoparticle, you get very broad peaks in a powder diffraction pattern. Also, microstrain gives rise to peak broadening. So microstrain is where different parts of the sample have got slightly different unit cell parameters, perhaps because they've got slightly different chemical contributions. So the way that we think about the peak shape in the fundamental parameters approach is we try to describe all the contributions from the source, all of the contributions from the instrument, and then the contributions from the sample, and we mix those together to produce the overall peak shape. The mathematical way that we mix them is called convolution, but as I say, we'll go into that in a later video. So let's go to my desktop, and if I go to my desktop, I've got a folder open here where I've got the basic input file that we created when we did the Rietveld refinement on yttrium oxide in a previous tutorial. And you might remember that we had an R factor of something like 14% for that refinement. So just to check everything's still working as it should, I'm going to launch Topaz and I'm going to do the Rietveld refinement against the yttrium oxide data again. Yeah, and as we had previously, we've got an R factor of 14.2%. It's a very nice Rietveld fit, but if we look in detail at the peak shapes, we're not quite picking up the peak shapes of the low angle reflections correctly. Okay, so what can we do about that? Well, what we can do is, as I say, come up with a slightly better way of describing the peak shapes using this fundamental parameters approach. So rather than using a simple axial model to describe the beam hitting the sample, I'm going to comment that part of the input file out, and I've pre-typed in a full description of the diffractometer that's actually appropriate for this data set. So I've got the radius of the diffractometer, something about the divergent slits, something about the X-ray filament length, something, for example, about the solar slits, something about the slit that was used, the detector slit that was used. So these various lines describe the instrumental contributions to the peak shape. Later on in the file, I'm going to get rid of the empirical peak shape that we used before, which was this TCHZ line. And instead of the empirical sample peak shape, I'm going to describe the peak shape in terms of 2 macros, which describe either size broadening, which is this term here, or strain broadening of the sample. And initially, I've got the size of the sample. This number here says that the Gaussian contribution to the size broadening is appropriate for a 10,000 nanometer sample. So that's a very, very big coherent diffracting domain, and the Lorentzian contribution to the size is also appropriate for a 10,000 nanometer particle. The second macro here is the strain macro, and again the Gaussian contribution to the strain is a very small number here, and the Lorentzian contribution to the strain is a very, very small number. So with a large particle size and a low particle strain, the peak shape that we should calculate should be entirely appropriate for just the instrumental contribution. What I'll do is I'll send that refinement over to Topaz, and we'll now just do the refinement with purely the instrumental component. My R factor now is a lot higher, it's 36.92%, and that's because we've got no sample contribution to the peak shape. And you can see, particularly at high angle, the peaks are calculated much sharper than we observed them experimentally. So if we go back to JEdit, we can add in the sample contributions. So I'm just going to turn on the Lorentzian size component and the Gaussian size component and the Lorentzian strain and the Gaussian strain, and just try refining all of those parameters together to see if we can improve the peak shape. And so if we do that, if I run through the refinement, what I find is my R factor comes down significantly, and it's come down to 13.2%. You may remember that's a lower R factor than we got with the empirical peak shape approach. We're now doing a really nice job of fitting the peaks at high angle, and if I go to low angle, we're actually picking up the asymmetry of these peaks beautifully. So this instrumental description, along with a sample contribution, is doing a really nice job of fitting the diffraction peaks. If we go back to the input file, we can look at the values that we've extracted. And in fact, if we look at this, we can see that if we look at the strain, there's a large contribution of the Gaussian strain, and there's a much smaller contribution of Lorentzian strain. So it may be that the Lorentzian strain isn't actually important in our model. So if I fix that quantity and I just put it back to a very small number, we'll try that in our model. And also, if you look at the size, the Lorentzian size contribution is a small number. That's a significant broadening. But the Gaussian size is a much larger number. And Topaz has warned us it's gone to a limit. That means that that parameter is not really very well defined by our diffraction data. So let me just try fixing that parameter and putting it back to a large number, essentially an infinite particle size, 9,999 nanometers. And let's just try refining the data with that model. And again, if I go through the refinement now, my R factor started at 13.18%. Now I'm using 2 parameters fewer, and actually I'm getting a very slightly better R factor. And that's because we've removed some of the correlations in the least squares by removing parameters that aren't actually defined by the data. So at that point, we've got a beautiful fit to our diffraction pattern across the whole range of 2 theta. And the wonderful thing at this point is we're only using 2 parameters, 2 free parameters to describe the peak shape. And those parameters have got physical meaning. And the physical meaning is the size and strain in the particle. So for example, this number here is called L vol. It's actually formally defined as the volume weighted mean column height in your sample, but it can be related to a simpler parameter like the size of the particles. So there are some online tutorials on my webpage which go through this in more detail and tell you how you can relate a quantity like L vol to the particle size. So hopefully that tutorial has been useful. Hopefully it's given you some flavor of this idea of fundamental parameters fitting, and it's shown you that you can fit your peak shapes using physically meaningful quantities that can give you a more efficient refinement, a better refinement with fewer parameters, and also parameters that actually have some physical meaning. Hopefully you found that useful.